Okay, so this is going to lead into another video that's already been created, which feels kind of weird because I'm making a video that goes before one that's already been made. It's kind of Inception-like. Like this is a video almost inside a video, but not quite. It's just confusing and terrifying to me, but that's okay. All right, so the first thing we're going to do with this is we described the situation already where we have this cart that's moving along and it's got a mass of 2m, and it's going to be colliding with another unsuspecting cart here that just has a mass of m. And then as they collide, this spring plunger on the front is going to compress some, and as it's compressing, it's applying an unbalanced force to this cart to make it speed up, but that spring plunger also applies an unbalanced force to this cart to slow it down some. And then at some time later, that plunger re-expands and the two carts shoot apart. So the first thing we're supposed to do, is kind of find the maximum distance the spring compresses if the spring has a spring constant k in terms of m, v0, and k. So we're supposed to figure out how far that thing compresses. All right, well that kind of begs the question of where do we begin with this thing? Because that's kind of a little bit more advanced question. And I probably should end that question with a question mark. All right, so when all else fails, we always go back to step one, pick a system. I think it looks like I've already picked a system. Our system should probably be the two carts. Okay. Step two, look at the interactions. So we've got system. We're going to look at interactions next. System, interactions. Look at what forces are acting on this system. External forces acting on this system, we've got normal force and gravity, and we've got normal force and gravity. Neither of those two is external and unbalanced. They're both external forces, but they're not unbalanced, so they're not going to cause a change in the momentum of the system, which means we already kind of got a hint towards part 3. Part 3 is model. Part 3 says we figure out what mathematical models, what physics concepts apply to this. Well, if there's no external unbalanced forces applied to your system, what is conserved in that system? Okay, our class very wisely said, in this entire process, momentum is conserved. So nowhere is any force that is external and unbalanced applied. So momentum is conserved in all three pictures. It's conserved in this entire thing. That's a huge, valuable concept. Okay. The second thing you'd want to check with this situation is, as I'm looking at any forces that are being applied, gravity and normal force, neither one of those two does any work. The spring applies a force as both of these things are traveling a distance, and that spring's force is horizontal, and these two objects are moving horizontally. So the spring does work on this system. Is the work done by a spring conservative or non-conservative? Conservative. Work done by a spring is conservative, which means, based on that idea, mechanical energy is conserved throughout this problem. Now it might change form, might change from kinetic to spring potential, or from kinetic of one object to kinetic of another object, but the idea is that the total mechanical energy is conserved throughout this problem. Those are our two huge models that we're going to apply that are going to let us get through everything on this. And sometimes we're going to apply those two models simultaneously. Okay, but that's the thinking. When you first sit down and you get something and you don't know what to do with it, those are the things we have to start with still, always. Pick your system, look at what's interacting, and then figure out by asking those two questions. Are there any external unbalanced forces acting on the system? No. Well, then I know I can use conservation of momentum. Are any forces doing work on the system? Yes. Okay, well, are those forces conservative or non-conservative? If they're conservative, then you know you can also apply conservation of mechanical energy. Okay, so finding the maximum distance the spring compresses, if the spring has a spring constant k in terms of this stuff, is our first thing. And so in this class, right before we started filming this video, we did a demonstration in the year we're filming this with Nicole, the excellent slow motion runner, who we compared, and I think even have a picture of something like this on a previous slide. Yes, person 1 and person 2. And we came to these conclusions. Nicole is person 2, I think I am person 1. Is that as person 1 is running faster than person 2, the distance between them decreases. As person 2 is moving faster than person 1, the distance between them increases. And when they're moving at the same speed, the distance between them is not changing. Okay, so when we're thinking of taking this picture and moving it on to this situation, at first, person 1 is moving faster than person 2. So what's going to happen to the distance between these two, even as that spring is compressing? What's going to happen to the distance between this cart and that cart as the spring compresses? It's going to decrease. What's going to happen to, I guess, after these two separate, it seems likely that car 2 is going to be moving faster than car 1, or as the spring expands, that spring is pushing this one forward and this one backwards, so it seems like car 2 should eventually be moving faster than car 1, so the distance between them should increase. We're trying to think about then, when they're moving at the same speed, or when this thing is at I just answered my own question. When this thing is at its maximum compression, what's true about their relative speeds? That's the piece we want to think about. And I'm going to pause the video so I can ask that question better. All right, despite me stumbling over my words, this class just figured out what I was trying to get at, which is that the spring is at its maximum compression at the instant these two things are moving at the same speed. When 1 is moving faster than 2, the spring's still compressing because 1's getting closer to 2, if it's moving faster. When 2's moving faster than 1, the spring is expanding because, and the distance between them is increasing, because 2's moving faster than 1. So the closest they're ever going to get is the instant when these two are moving at exactly the same speed. Well, that makes some math very easy for us, because since momentum is conserved this whole time, and we're looking for the instant these two are moving at the same speed, we can just say m1 times v1 plus m2 v2, that's before they collide, is equal to m1 plus m2 times v when they're moving at the same speed. This v is the speed at the maximum compression. For what we just described. Okay, so we can figure out that speed. Before they collide, v2 isn't moving, so this has no momentum. Before they collide, m1, who has a mass of 2m, is moving at a speed v0. And afterwards, this total system has a mass of 3m, and it's moving at a speed v prime. We can solve for v prime pretty easily. Okay, this is our speed when the spring is at its maximum compression. And that's all fantastic, but it didn't answer the question. What we're looking for is, what's the maximum distance the spring compresses? Well, we started off by saying there's two big ideas we're going to apply. We just applied momentum is conserved. We also have the notion that mechanical energy is conserved in this system throughout. So if I'm looking at the kinetic plus potential here, it should equal the kinetic plus potential here at the maximum compression. So let's look at the different kinds of energy we could have. Okay, so I'm going to say that mechanical, I'm not even on pen drawer, or maybe I am. Mechanical energy in picture 1, which is just like when car 1 is moving by itself, plus work non-conservative, which we already said was 0, has to equal mechanical energy at location 2, which is our maximum compression place. Okay. We always want to think about our three different kinds of energy. Kinetic energy at location 1, spring potential energy, gravitational potential energy. And we want to compare those to kinetic energy at location 2, spring potential energy at location 2, gravitational potential energy at location 2. Okay. Gravitational PE, we don't care about. This thing isn't changing height at all, so there's no change in gravitational PE. in our first picture, is there any spring potential energy here? No. So we don't have to worry about that part. There's no PE spring. So really, we're just down to looking at the initial kinetic energy of the system and setting that equal to the kinetic energy at this maximum compression place plus the spring potential energy. So we'll go ahead and pause the video and plug some stuff in so this video doesn't become incredibly long, and then go from there. I'll show some of my algebra just so you have a record, so in case you make a mistake you can catch it. So I plugged in for for the mass, 1/2 times 2m times v0 squared. I cancel out a 2 there. And then here, I multiplied this 3m times the 1/2 to get 3/2 m. I squared the 2, so that's why I got 2 squared. I squared the 3, so I got 3 squared. I squared the v0, so I got v0 squared. And then I'm going to cancel out a 2, and I'm going to cancel out a 3. And so I get mv0 squared equals, looks like 2/3 mv0 squared plus 1/2 kx squared. And then I'm on my way to solving. And we'll check to make sure I get all the way to the end of this. Let's get this down a little bit. So if I move this 2/3 mv0 squared over the other side, I get 1/3 mv0 squared is equal to 1/2 kx squared. If I multiply by 2, I get 2/3 mv0 squared over k is equal to x squared. And so I think x is equal to radical 2/3 m over k times v0. I'll just put the v0 squared under the radical. So I think that's what we get. Okay, so our class, eventually we all ended up right about here. And that's good and that's correct. We verified this a couple times over. And so now we're ready to move on to part B, which is find V1 after the collision, V2 after the collision, and we've already answered this part. So our next section of this problem is now these two, after the spring has hit its maximum compression, it begins to re-expand. So now the two carts are going to separate apart from each other. And so we want to know when they're separated apart, when they're no longer interacting with each other, how fast are each of these two moving. But that is a much more complicated problem that's going to require more than the roughly 2.5 minutes I have left for this video. Luckily, I've already made the video that comes after this. What? Yeah, so we'll watch that one in just a second here.